Okay, so we looked at a simulator just like super briefly last time that I will go back to, and I may not have shown it to this class, and the one I did show it to, we had like 2 seconds to do it. So here is a link. It's to the link layer addressing and forwarding tool, and it's on that sheet that's in your extras folder of all of the simulations for our book. So what this diagram does is, like a lot of these other simulators you've seen, every time you open the page, it comes up with different numbers and a different question. And so what this is basically doing is telling you your task is to send something from this computer to that computer. And in this particular case, we're trying to send something from A to B, it says here. So A is here and B is up here. So it's going to have to go through a router and a couple of switches, and there's a bunch of other computers around here. And they're asking you, give me the source and destination IP address and Ethernet frame addresses at points 1, 2, and 3. So these aren't devices or exchange points or electronic or anything like that. They're just saying, if I used Wireshark and I were to grab the packet that you are sending from A to B at this point, at this point, and at this point, what would you see? And so the thing that you need to realize that is how this stuff works is that we have layer 3, which is the IP address, that's worried about connecting things end to end. So if this is A and this is computer B, in every frame, everywhere along the way, your source and destination IP addresses will never change. They will be A and B, whatever the new numbers really are. Those aren't real IP addresses, of course. Right? So anybody that gets this packet along the way, this router, this router, this router, they will all see that in the IP header, there's a place to put the source address and there is a place to put the destination address, and it will be filled in with the sender and the ultimate destination. So I go to my forwarding table, or I've run my routing algorithm, and I ask my forwarding table, say, I have this packet that needs to get to B. This is happening inside this computer over here. So I look at my forwarding table, and he says, you know, what port should I send this packet out of to get it one step closer to B? Well, in the case of this computer, it looks like it's obvious because I only have one connection, so it's, you know, going to be always. But the forwarding table doesn't just tell me send it out over this wire. It also says send it to the following IP address, R1. So if you will give it to router 1's IP address, he can get it from there. So what does it mean to give it, why that one? Because these two guys are on the same LAN as each other. And you can only see devices at Ethernet layer, at layer 2, that are on your local LAN. So I can't see anything from this computer except what's on this local LAN. So if my forwarding table had come back and said, you need to send it to this router over here, I would be in really big trouble because I can't get to it. It's impossible. So the only thing my routing table can have is the IP address of something else on my local LAN. Always, no exceptions. Right? So for a PC, most of the time, it's always going to be the same one place because I only have one connection. But for routers, you know, routers can have dozens of input cards and dozens of output cards. And so your routing table can be quite sophisticated. And based on the destination address, it could send it over any of a number of links. But the router is going to do the same thing. He's going to look in his forwarding table, and he's going to ask the forwarding table, hey, where do I send a packet that I just got, somebody knocked on my door and threw this packet in, and it needs to get to B. Where do I send it to get it one step closer? So this is a LAN, and every one of these other ones is a LAN, a separate LAN as well. So what my forwarding table is going to tell me to do is, in this particular case, the LAN that I want you to drop this packet on is this LAN here, and I want you to send it to this guy's IP address. So in this case, the IP address is going to be that of the interface on router 2 that sits on my LAN. And then when router 2 gets it, his forwarding table is going to tell him to send it to, out of all the LANs he connects to, send it to the IP address of the port on router 3 that belongs to my LAN with me, step by step by step by step. So let's say I start off and I get that advice. Let's say I look in my forwarding table at layer 3, my IP software, and I've been running Dijkstra's algorithm, so I built myself a tree, and I've built myself a routing table here of all the networks I know how to get to and the port I'm supposed to leave on, and I've learned the IP address of this router a long time ago. And so my forwarding table says, trying to get to B, you need to send it to IP address equal router 1, and the port on router 1 that's on your LAN, LAN 1. So we'll call this LAN 1, and we'll call this LAN 2, and we'll call this LAN 3, and this will be LAN 4. Okay? So send it to the IP address, because this router's got lots of IP addresses. It connects to lots of different LANs, and each LAN has a different range of IP addresses. So every one of these ports has a different IP address that belongs to a different subnet. So I want to send, from my PC anyway, I want to send it to the IP address on the port that this, out of all the ports this router has, that connects to my local LAN. So the IP address he has is going to look very similar to the IP address I've got. It's only going to change at the end. If it's like 128.249.27 and I'm .116, he's probably going to be like .254. You guys ever program the little routers you have at home? Try testing them, open up a web page to them. They almost always end in .254. But they're on the same LAN, right? So they have, the rest of the number looks the same. Over here in this network, totally different network. 66.30.14, it's a /24 network. So this guy maybe right here has a .20, and this guy maybe has a .21. But they're both from the same network, but it looks nothing whatsoever like this one over here. Totally different network, totally different LAN. So my forwarding table has now told me where it is I need to send this packet. The next device along the journey to P that will help me get this packet to B is the packet with this IP address, .254. Okay, so I'm going to build this packet and I'm going to drop it on my local network. Well, not so fast, because this is just the IP datagram. You can't just drop IP on Ethernet. You can drop Ethernet frames on an Ethernet network, but an Ethernet frame basically looks a little different than this. An Ethernet frame is going to take your entire IP packet, the source and destination address, plus all the extra payload. There's all the data in here as well. We're just super focused on the addresses for now. And it's going to send that whole thing for you across the network, across the LAN. But you're going to have to tell him which Ethernet address to send it to. So not only do I have an IP address, but don't I also have a hardware address? I have a layer 2 address. It's built into my computer. If I come up here and look at the one I've got, today I'm connected to Ethernet. So if I open up my network preferences and I choose Ethernet and I go to hardware, there's my hardware address. And my IP address is totally different. Looks like that. I can move around campus and move around Houston, and my IP address will change for every single new LAN that I'm part of. Every time I get into a new subnet, I'm assigned an IP address from that subnet. So this IP address can change 100 times a day. This will never change. It's hardware. So anytime I send an Ethernet frame, I also know this address because I include it here. So at layer 2, I'm going to switch colors. At layer 2, I have a MAC address. So this is Ethernet layer. And my MAC address look like, over here, 036A2Z. It's this weird hex thing. It's 48 bits long. We could have written it as decimal, but then it would be very confusing to see which one was IP. So let's say I'm going to end one in 6B, and this one ends one in 2F. This time the MAC addresses have nothing whatsoever to do with each other. They have nothing in common. There's like no concept of the same network they belong to or network numbers, because that implies it can be changed so that they're grouped together. This is like a serial number out of the factory. It's unique. There's no reason to believe that you put 5 computers on a LAN that they will all have consecutive serial numbers from different manufacturers. That just is not going to happen. So these are hardware addresses. So it's time for me to build my Ethernet frame and send it. And I know my source address. My source address is 6B. It's much longer than that. I'm just writing a couple of the characters. So this is my source Ethernet address. But what's my destination Ethernet address? Well, it's the hardware address for this router. Well, what do you mean this router? Well, I mean this IP address right here. In fact, I should draw this in orange to kind of stay consistent. This address belongs right here to that orange dot, and this address belongs to this orange dot. So how do I know the IP address because my routing table told me with its routing algorithms, this is the IP address that you need to get it to. But I don't have room to put that up here because this is already taken up. I need to put it in my Ethernet frame, so it will go across the LAN to this physical device. But how do I know what the destination hardware address is when all I know is the IP address? There's a protocol to figure that out called Address Resolution Protocol. You broadcast it out on your LAN. Every single device on the LAN hears it. They all have to implement ARP, so they all pick it up. They all look inside the ARP payload, and they see what you're looking for is the hardware address of whomever it is on the LAN that has this IP. And in this case, it belongs to the router, and the router will answer back, I'm here. Here's my hardware address. I'm the one that has that IP. So if you're trying to send an Ethernet frame to me, here's the hardware address you want to use. And if you do that, you will in fact be getting your IP datagram to that IP address. So fantastic. So I learn what it is from ARP. ARP helps me fill this in to F. And now I can send the frame from here over to here. And when it arrives at that Ethernet frame, the system checks out, yeah, this is for me, all right. Okay, great. Everything looks in order. It decapsulates this packet and hands up to IP this packet. So now inside the router, it knows it's coming from A and going to B. It has no idea what routers it went through between here and there yet, but it does have the task of figuring out where to send it next. So it will look in its routing table, and it will be given the IP address of this. What did I decide it was? I didn't give it one. 66.30.14.2. That is what we call the next hop. And that belongs to this guy right here. And so my forwarding table is going to tell me at the IP layer, you want to send it to this IP address. Not sure how you do that, but that's who you want to get to. ARP to the rescue. I broadcast out a request on, this time on LAN number 2, saying, who owns this IP address? Please tell me. And the second router, along with all the other devices on this LAN, will hear that request, and the second router will respond saying, hey, that's me he's looking for. Oh, okay. Here's a packet back. It's an ARP reply, and it says, here's who I am, and here's my hardware address. It's like, great. So they build a second Ethernet frame. This time the Ethernet frame is going from this guy's hardware address. It's a different port on the router. So not only does it have a different IP address, but it has a different MAC address as well. So this time it's A6. And the destination hardware address, it's just making stuff up here, E9. Right? So it's going from and to a different hardware address. So your packet goes between layer 3 devices, hopping its way across the internet, LAN by LAN, and it does so by going from the hardware address of the sender to the hardware address of the recipient. At each step along the way, you flood the local LAN with your packet. Everybody's hardware network card looks at the packet, looks at the Ethernet frame, and says, is this my hardware address? If it isn't, ignore it. If it is my hardware address, pick it up and hand it to IP and see what he wants to do with it. Okay, you can never see a hardware address that is not on your local LAN. So even if someone told you the hardware address for this device here was, 3.5, I'm going to use letters because it keeps it from being confused with the IP address. 3C, it wouldn't do you any good. The only person that can benefit from that knowledge is this guy here. So only when it's inside this router is that helpful. So let's go back to the diagram and take a look at what's happening here. So I'm sending from A to B in this case. Here's my hardware address. Here's my IP address. They put the hardware address on top. I would usually put on the bottom, but you can tell what it is because it's hexadecimal. And this one has got periods, and this one will have hyphens or colons. Usually you'll see colons. So if I'm going to send something from A to B, I've got to go through this router, right? How many LANs does this router connect to? 3 that I can see, one on the left, one on the top, and one on the right. It's going to have 3 different subnet ranges, and it's going to have a different IP address on each one of these interfaces, and it's going to have a different hardware address on each one of these interfaces. Somebody went and bought an Ethernet card and put it on a, soldered it in and programmed it and did all that here, here, and here. So if I'm going to send this off, what I have to do is let my routing software say, how do I get something to a network that's not on my local LAN? And your forwarding tables is going to say, give it to the router. And it's going to do that by saying, give it to 128.119.88.147. And so then you're like, okay, but Ethernet doesn't use IP addresses. And this is an Ethernet network. So I need the hardware address of that router. Well, use ARP. You broadcast out an ARP request with that IP in it, and whoever owns that IP will respond back with their hardware address. And then you'll have what you need to build an Ethernet frame. So you can see this all the time on networks, and if we're lucky, depending on how they have this isolated, they may have only my traffic on my leg of the LAN. We'll see. I'm going to try opening Wireshark. No. Feels good to crash Wireshark. It's actually kind of hard to do. So I wear it proudly as a badge. All right, here we go. I'm going to open Ethernet, and what I'm trying to do is filter for ARP. Here's a broadcast, so here's some ARP packets. They're coming from Dell devices. Who in here has a Dell? You do. Could be coming from yours. Do you know how to look up your hardware address? Anybody else have a Dell in here? If you do, be looking up the hardware address and see if it ends in 23. So whoever has this Dell address, they are sending out ARP requests, asking a couple of different questions. One of them they're asking is, who has 172.26.62.56? And he has this question because IP has tapped ARP on the shoulder and say, can you go find out who has this IP address and give me their hardware address? I need to send them an Ethernet frame. And so it is broadcasting out some requests for that. And now it's asking for a different one. Maybe it's got a packet it needs to send to them. Here's a third one that it's trying to look for here. It's all kind of unusual. Could be something fishy going on. But these are all ARP requests. And if we stop and we go look at one of them, it says address resolution. You notice it's Ethernet and then ARP. There's no IP in between. So this is a packet that gets sent out when ARP and when IP is stuck. IP can't send its packet out yet because it doesn't know what hardware address to put in. So what happens is it's coming from the Dell, but it's going to everybody on the LAN, so it's being broadcast to everyone. And inside this, I said, look, here I am, here's my hardware address and my IP. I'm trying to get to this IP address. But this is all blank because this is what I need somebody to fill in. Oh, please, won't you help me fill this in? So everybody on the LAN picks this up and has to look inside, and whoever is responsible for this IP address should answer. And they will change the type from a request to a reply, and the sender becomes the receiver, and the receiver becomes the sender, and they fill in the missing piece of data. So we can close this up and pull open a different one. Let's see here. it that one that I want? They have to be connected to my local Ethernet network. Unless the Ethernet and the Wi-Fi are all part of the same switch. Depends on how they built it. But probably, you're right. Probably these are not, which is why I get much better performance from Ethernet than I do when I'm on Wi-Fi. Or it's this, 10-year-old dinosaur. Take your pick. I do have an ARP file in here. I caught an ARP storm at a hotel, the hotel I stayed at a bunch of times in Mexico. So here in the period of 10 seconds are hundreds of ARPs. And they're from a variety of different devices. These are the names of the manufacturers who were assigned that range of MAC addresses. This is not what the MAC address really looks like, but Wireshark goes and looks it up for you to kind of help speed things up. So the hardware address really is 6400F1, but if I were to go out here and say, look up MAC address, vendor, MAC address lookup here, and I were to ask Z6400F1, 6400F1, and say look up MAC, and then it was licensed to Cisco systems. So they just said Cisco for me to save me some time. And it was sent to an Apple device. And so there's a bunch of requests in here. Who's got this address? Tell this person. So these are people who have IP packets they're ready to send, and they need to know what's the hardware address of the device on the local LAN that my routing protocol thinks I should send it to next. Okay, if you see something in here called a gratuitous ARP periodically, this is an ARP that is sent from you for you, and you drop your source hardware address in here and your source IP, and you broadcast it out on the network to everybody on the network, and you fill in knowing full well the only person that could answer this question is you. You send a question to yourself by sending it on the network. But there's a reason why you do that. When you send this out, everyone gets a copy of it, right? They all have to run ARP. They all grab it off the network because it was broadcast to everyone, and they pull it up, and one of the things they do is they accumulate information about the network. They're snoopy. And so they notice, this isn't for me, so I'm not going to answer it, but it's good to know that there's this device out there, this Hewlett-Packard device with this hardware address and this IP address. And I'm going to write that down because who knows, maybe in a minute, IP on my machine is going to ask me for that guy's hardware address. And if he does, I got it. I don't have to ARP for it. Somebody else did, and I saw a copy of it. So you're always making a list of all the devices on your LAN. All the devices are doing this all the time. So you don't have to ARP as often. So once you learn where somebody is, what their IP and hardware address are, you write it down in an ARP table, and you set a timer, and it expires. It has a time to live, just like everything else we've looked at all semester long. And this one is called the gratuitous ARP, and it's sent when a device changes its IP address, and it wants everybody on the LAN to know so they can get rid of the entries they may have had for it. Or if it's a new service that's being introduced on the network, like in this case, a printer got turned on, and they want to broadcast out to everybody, hey, in case you need a printer, here I am, and here's my hardware address, just in case you need to know. So everybody will make a note of it. So this is a trick way of getting your entry into all the devices on your local LAN. All right, but all this stuff is just on a local LAN. Okay, back over to where we were. So when it leaves my computer, it will come from my IP and hardware. What will be the destination IP address if it's trying to get to B? If I'm trying to send a packet from A to B, the packet is leaving A at point 1 on this diagram. I look at the packet. What's the source IP address? It's me. What's the source MAC address? Also me. What's the destination IP address? Is it the router or is it B? At the IP layer. It's the destination, it's B. Even if it goes to 1,000 routers, if it's not B, how in the world does the router know where you're trying to get to? And if it doesn't know where you're trying to reach, how does it know which way to go? Anybody seen John Candy and Steve Martin in, what was the name of it? Oh my God, I can't believe I'm thinking of all the other comedies, not Chevy Chase Christmas Vacation, not Dirty Rotten Scoundrels, not. So in this, it will come to me in a second. I'm getting old. So in the scene, John Candy has fallen asleep at the wheel after giving Steve Martin a ride across the country, and Planes, Trains, and Automobiles is the name of the movie. And somehow it's like in the middle of the night. There's nobody on this country highway, and John Candy turns around and manages to drive the wrong direction, but he doesn't know it because there's a divider and he can't see the road. So he thinks he's like. So this car pulls up next to them as they're driving down the road, and these people are like panicked and freaking out because they're going the wrong way, right? And they start screaming out the window, "You're going the wrong way!" And Steve Martin kind of sees him and wakes up and like, "What?" They roll the window down. He goes, "You're going the wrong way." And so Steve looks over at John and he says, like, "They say we're going the wrong way." And John says, "How do they know where we're going?" Right? So it's all context. It's all sort of which abstraction. So if you don't know where you're going, how can you get there? So you can't change the destination address for IP. He's right. It's B's IP address. That's what you'll find in the packet at point 1. But what about the destination hardware address? Can it belong to B? Why? It's just that simple. You don't need to know any other sophisticated answer than that. It's just not on my LAN. I can't see it. Period. Doesn't matter, well, it's the last hop, or it's 3 hops away, or, you know, you're going to hand it to the, no. It's just not on my local LAN. You can't see any hardware addresses that are not on your local LAN. I promise. So the only way to send it to this guy is to send it to his hardware address. Do you send it to his IP address? No. The IP address was already taken care of up here. You have space for 1 IP address source and destination, and you have room for 1 MAC address source and destination. 3 of them are full. The only one left is the destination hardware address. It goes here. So I'll give you a problem or two to play around with that. But that's a big emphasis on the hardest part for people to kind of remember about it. So that's what these slides go through. They basically explain what we've talked about. The slides may be a little more helpful to you in kind of understanding what's going on. And they're going to show that, you know, once it's inside the router, it's not on any LAN at all anymore. It's only on a LAN when it's being transmitted from one place to the next. So when it's not on a LAN, why would you still have Ethernet stuff? So once it arrives at this router in the middle, the first thing it does is throw away that dark blue Ethernet wrapper and leave you with just that light blue IP datagram. Then the router looks at it, he makes a decision over which next LAN it needs to go to, and will ARP to find the destination IP address's MAC address, and will build a new Ethernet frame with that information in it. So this kind of steps you through in excruciating detail about what that looks like. Okay, do you guys feel like you followed that? You feel okay about it? Did you ever figure out your hardware address?
Yeah. Well, I mean, it's just like a bunch of.
Yeah, but I wonder what like the last 2 numbers were. Do you remember if it was 33? Because that's what it was when we looked at ARP. Because he's got me wondering whether I can see things on Wi-Fi in here. Or...
33.
It is the last, so we can see him. Do you know what's your Salute. Can't be in the same subnet. However, here's potentially a complicating factor. You can have as many different subnets assigned to a LAN as you want. Doesn't have to just be one. So for example, we use private 10 dot addresses in lots of places, lots of businesses, things like that. But if everything has a 10 dot address, how would anybody ever get to your web server? it's not legal. So for some of your systems, they're going to have more than one IP address, a public IP address, and like if they straddle both sides. So therefore, if the same machine has two different IP addresses, it's connected to two different subnet numbers, but it can do that with a single cable. And routers can do that as well. So you can actually have as many as you want. It needs to be isolated with a subnet mask and unique, but it's okay to do that. And that's a way to merge companies. When there's lots of oil and gas merger and acquisition activity, you get really good at figuring out when you're called at 11 p.m. on Sunday night, the night before, and you're told Monday morning at 6 a.m. we're going to announce to Wall Street a $42 billion deal to buy Baker Hughes, and you have until 8 a.m. to merge the networks. I don't want a single thing leaving Baker Hughes' network that does not come through our firewall after that point. And you're like, the first person you call is your Cisco SE. Time to get up. Got a little task. And it's not hard. I mean, it's tedious, but it's very straightforward. We've done it thousands and thousands of times. And you'll do things like that. You'll just put both subnets on the same LAN. And then they can coexist with each other. And your router tables will see both of them. And it will say, if something on this LAN is trying to get to something on that LAN, just drop it on the LAN and it's one hop away. It's on the same one. So it's kind of fun. All right, Ethernet is the name of the technology that we generally use. There were other topologies that were used in the past. Some of them, everybody connected to the same single cable. That's the way Ethernet first worked. These days, however, most of us have our own individual cable, unshielded twisted pair, Cat5, the little click sound that you put in, and we connect to our very own individual port on a switch. So why use the switch? Because on a shared bus, you see all the traffic, all of it. Most of it is presumably not for you. So bandwidth that you could be using is taken up in part by everybody else's garbage. If you ever had the feeling on the road, this is a way to tell if you're a type A or a type B personality. If you are a type B personality and you're running late for a meeting, you will say to yourself, next time I will leave 10 minutes sooner and plan for this possibility of bad traffic and do a better job of managing my time. You're type B. If you're type A, it's like if everybody would get the hell out of the way, I could get to where I'm going. Right? So you're a type A personality if that's you. So on the network, if you find that other people are using your bandwidth and you're kind of type A, you're going to move over to this star configuration where the total amount of bandwidth that can leave and enter the network won't change, but it's quiet on the home front. You're never going to have collisions. You're never going to have to wait to send something. The switch will fix it. So if you just drop a switch into the middle of a congested network, 99% of the time the problems just vanish. There's lots of collisions that will just disappear. Okay, Ethernet has an interesting structure. Like all the other layers we've looked at, it adds stuff to the front of the packet. So in this case, I have my source and destination address, and I have a type here that says, who is this going to be given up to up above? Is it ARP? Is it IP? Is it OSPF? Is it something else? And then here's the actual payload. So if this is an IP datagram, this will say type 8 IP, and here's the data. And we can see that. I'm going to let Wireshark pop back up here while we're talking. But this is where the rubber meets the road. This is the layer where you are actually converting ones and zeros to whatever electrical or optical or radio wave technology the medium your network uses requires. So what you're going to be sensing at this layer are like voltages or lights blinking on and off, and you're supposed to determine whether that's ones or zeros or what's going on. So with Ethernet, because it's basically like an endless stream of ones and zeros with frames following behind each other very closely, when you look down at the wire and you just see all these millions, hundreds of millions of ones and zeros a second going by, which is what a 100 megabit network is, 100 million of these things going by every second, how do you know where the beginning of one of your frames is, let alone whether it belongs to you or not? I mean, it's not like one of them goes by waving a little flag like at the beginning of the Olympics, Sweden and all the Swedish athletes are following. You don't get that. But what you do have is a pattern that you can look for that is prohibited to exist anywhere else in any of these frames except at the very beginning of a frame. So when you see this pattern, it's telling you I'm the beginning of a frame. And it's 7 bytes of alternating ones and zeros, and the 8th byte is alternating ones and zeros except the last 2 bits repeat 1. So it's 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0. That's 4. 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 64 bits go by, you better be ready because the very next bit is the start of your Ethernet frame. Okay? That's so long and so irritating that people truncate that preamble, and they just make it shorter. It also serves a very important purpose. If each of you have a 100 megabit per second Ethernet card, you will have a crystal that is oscillating 100 million times a second to sort of tell you when to expect the next bit and the next bit. But we don't want to pay for perfect crystals, and so they don't oscillate really at exactly the same rate. You know, the 100 millionth one on your side may have to hang a leg out and like hop on one leg. So you will use these bits as well to synchronize your clocks to keep from drifting apart. So the analogy I always like to use is, say you're at the restaurant, you have two mariachi bands, and you lower the curtain between the two of them. They're playing the same song, and you raise it back, a soundproof curtain, you raise it back up. Are they still going to be at the same point in the music together? Well, yeah, if it's 1 second, yes. What if it's 30 seconds and you come back up? They're both professional musician groups. Are they both going to be on the same note on each side? Probably not. One of them's probably drifted a little way from the other. So this happens on communication networks as well. And now I'm hungry. See how good that did me? Okay, so you'll synchronize things. Ethernet is unreliable. It doesn't bother asking permission or having a handshake or anything like that. So why do it? Because it's crazy cheap, and anybody that wanted to could implement it. What we had before this was painful and expensive, and you had to pay license fees to have a card that would connect to it, and it was expensive, etc. So, you know, if you're willing to go cheap, then great, but what it basically means is you're going to have no way of knowing whose turn it is to talk next. So you're just going to have people just barging in and just trying and figuring it out and seeing what's going on. This is like at the intersection out here at Elgin where the lights blink red. You know, there's like straight and left turn on all four sides. So there's 8 possibilities of who could go next. And people do not agree. And you hear horns honking and stuff like that. That's exactly the way this is supposed to work. And it's also unreliable. So if you send a string of those ones and zeros I talked about, hold on to a copy of them for a minute. There may be 12, 15,000 bits in the whole packet, because if it doesn't make it to the other end, you're going to need to resend it again. And we don't want you bothering the people upstairs. So just remember the last frame that you're supposed to send. And if you do notice that your frame didn't make it, wait a little bit and try again. And if it happens again, wait a little longer and try again. And just keep backing off and spreading things out. Everyone else will do that too, and you will find the way to get things through. So that's called binary backoff, and we'll talk a little bit more about it. So there's a bunch of Ethernet standards. They're all kept up by the IEEE, and they're all part of the 802.3 standards. Ethernet has proven to be incredibly resilient. And 802.11 is part of this same group that deals with Wi-Fi, which is why we use MAC addresses for Wi-Fi as well. Otherwise, it's just crazy coincidence that both wireless and wired networks that we're most commonly using both have 48-bit hexadecimally addressed destinations. So that's sort of what's going on with ARP and Ethernet. Do you guys ever use Ethernet, or do you only use Wi-Fi? Yeah. Yeah, so it's rare, but it's much less error prone and usually better throughput. But we have so much bandwidth that even though half of what we send gets thrown away as collisions, you're still better off, and it's a whole lot easier. So why not, right? So that's kind of the idea. Did I give you guys the speech on why we send things, or how we send things digitally versus analogically? Have I done that one? Okay, let me step aside for a minute and I'll show you a parallel to what I just said with Wi-Fi. So in the beginning, when we had to encode signals, and this is the way, these are supposed to be even, believe it or not. This is the way radio and television and things worked as well. Amplitude modulation. What you would do is take the signal and perturb it, but perturb it by adjusting up or down the voltage it would have had at any given point, and send it across the network. And the person at the other end will remove the sine wave from it, basically, and they will have the signal you're sending, and it will be the reproduction of someone's human voice, for example, for the phone network. The problem with this is what really happens is as it goes along, the signal begins to attenuate, which means it gets weaker and weaker and weaker. And so every so often you stop and you re-amplify it. And when you do, you make it stronger again. The problem is that any noise that's been introduced into the line, which is always the case with copper cables because they're big antennas as well as great mediums to send ones and zeros, you amplify the noise as well. So the original signal that you sent at the beginning isn't exactly what arrives at the other end. This is why when you make an international phone call, sometimes the voice quality isn't very good because it's going through these conversions. But this is the only way we had of doing it for a long time. All right, so then Bell Labs made the decision, after lots of good science, that to send a human voice, they could send instead 8 bits, so a scale of 0 to 255. And if you did this 8,000 times a second, then what you'll basically be doing is at every one of these points, you'll be measuring 8,000 times a second what the value is here on a scale of 0 to 255 relative to the wave underneath it. And you're going to send those 8 bits instead. It's enough to reproduce a human voice. Okay, but no one changed physics and now makes copper send dots instead of red lines. It didn't change the way the molecules work. So what exactly are they doing? Well, what had happened in the meantime is electronics are constantly marching forward and improving and getting faster. So what we had at this point was a sine wave that looked much denser, much higher frequency. So you could use that to send a lot more analog detail, or you could say, you know, look, what I really need to do is, and it was orders of magnitude faster, what I'm going to do is change the pattern. So if it looks like this, it's a 1, and if it looks like this, it's a 0. So what you might be doing is having your analog signal applied on top of this. So what you'll be doing is this represents a 1, this represents a 0. So you're going to use multiple waves to do it. Here's the big advantage. If I showed you what I was trying to send was this, and what you got at the other end looked like this, I'm betting you would still say, you know what, this is still above the line and below the line, and this one's very noisy, but I'm going to call it above the line, and this one's definitely below the line. You will perfectly reproduce the 1010 pattern that they intended to send. So when it's attenuated and weak, and now it's time for you to re-amplify it, you don't re-amplify it, you regenerate it. You build a fresh new copy that sounds perfect. And so it arrives at the far end, an exact digital reproduction of what you sent. But it's not sent digitally. You're encoding digital ideas on an analog signal. It's the same wire, the same copper, the same light, the same airwaves that it's always been since creation. The internet did not change the way molecules work. Right? So the entire internet is still built with analog circuits. That's not going to change. What we're changing it is. So the analogy I would give you is if you've never made a photocopy of a photocopy of a photocopy of a photocopy, it looks terrible, right? But if you made a copy of a file and then made a copy of the file and made a copy of the file online on the computer, they're identical because you're making perfect digital reproductions of bits, not atoms. Okay, so that's a little bit about encoding. And so what we've got to figure out with things like Ethernet is how many of these bits can we get in there. So you intentionally dedicate a little more bandwidth, and that's why Wi-Fi is so tolerant. We're willing to use a network that has so many errors because it's so much faster that even with the errors, we still get great performance out of it, and it continues to improve. Okay, so what's an Ethernet switch? It's a device that sits in the middle of a bunch of these Ethernet-based devices, and it isolates you, so it does not allow any frames to go down the wire towards you that don't have your MAC address or aren't broadcasts. So how does it know what your MAC address is? Well, you could sit down and program the switch, but like a nosy neighbor that sits on her porch all the time, you also can learn by just observing, just watching what's going on. So what a switch will do is every time an Ethernet frame goes by, it will notice who it's coming from, and note on this wire, I just saw an Ethernet frame come and it had this source MAC address on it. Therefore, if anybody sends me a frame in a minute and they need to get to that MAC address, I know exactly which wire to send it down. That one right there. And I know not to send it down any of the other people connected to my switch. So that isolates traffic, and it also makes the switch what we call plug and play. You just plug the switch in and you turn it on, and within a moment, it will know where all the active devices are on the network. Assuming they're all sending Ethernet frames, it will. And so what you'll see is all the duplicate. If it doesn't know where you are, it sends it out to every single device, every single wire. But as soon as it figures out where you are, it will only send it there. So the competition goes way down. This makes them really popular and a cheap alternative to a router to kind of isolate what's going on a network. They're also completely transparent in most textbooks, meaning yes, they have Ethernet, yes, they have Ethernet addresses, yes, they have ports and all that, but none of that becomes an issue. It's all totally transparent. You don't see it, you don't need to worry about it. So anytime you see a switch, including in these diagrams, it means absolutely nothing. Ignore it. It's invisible. It will never change anything on your packets, as far as we're concerned. So that's why the answer was not, it has a source MAC address and the switch's destination MAC address. Now, if you put it on the LAN, it will see it, it will forward it for you. It'll deal with that. You don't have to worry about the switch's addresses. Just don't. And when it sends you something, it will lie and tell you it came from the router, even though it really came from this port on the switch. You'll never see the switch. You have no idea it's there, in order for that to be nice and easy to use. Okay, so what we do in a network is if there's collisions coming, like A needs to send something to A prime, and these are the port numbers that are labeled on the switch, all I have to do is just listen. So this is just going through what I just described. A sends something to A prime. What can the switch write down about it? He has no idea where A prime is, but now he's just learned where A is. He just saw a packet coming from A, right? So he's going to write down, I now know where A is. He doesn't know where A prime is, so he has to send it to everybody on the LAN. Once A prime responds, now he'll know where A prime is as well. So your computer is doing this all the time as well, so is your phone and your tablet. Any device that has a LAN concept and a MAC address is accumulating ARP hardware addresses in its ARP table. So that's what this is a ARP table. Okay, so in this case, now I don't know where A prime is, so I have to send it out to everybody. As soon as A prime responds and I know where he is, now he sends something back. Now I can add him to the table. I will never do that again. I will never send A prime's packets to C prime, B, C, everybody else. All right, so it's kind of beaten this topic to death. On a large organization like University of Houston, you will interconnect lots of these switches together, and this is when things get really, really interesting, because switches are a lot easier to manage and require less skill to do so. So switches are favored over routers because it doesn't cost you as much to operate them or to acquire them. So most organizations have hundreds and hundreds and hundreds of switches. We probably have well over 1,000, and maybe, who knows, 10 routers, something like that. They're just not that helpful inside of a LAN. And what you'll do is, if all of these are the same manufacturer, which is a trick the manufacturers use to get you to buy everything from them. So these things are basically an all or nothing proposition. You know, it's not like a place is going to say, I'm going to buy 30% of my switches from you and 40% from you, because there's a huge benefit you get if they're all the same. They will all talk to each other and share ARP tables, which normally you would need a router to figure out, like, this is a LAN. It's not the same LAN as this one. So if I needs to send something to A, normally that would be impossible without the help of routers. There are no routers here. So the way they get around it is they all share ARP tables with each other. And S1 will tell all the other switches, here are all the MAC addresses I can see. If you need to get something to someone that's got one of those, send it to me. So that's kind of routish, sort of, but it's all done at layer 2. So you build these trees, and they're called spanning trees, and they can be poorly managed, and you can end up with loops in your trees, in which case people will start advertising things to people they've advertised, and it will just mushroom on itself. It'll snowball. And Southwest Airlines had a catastrophic failure of their network that put them out of business for a couple of days. I mean, dead. Couldn't sell tickets, couldn't check flights, couldn't board planes, couldn't take off, couldn't load luggage, couldn't do anything. They were out of business for a couple of days. So just take their total annual revenue and divide it by 365 and just subtract a couple of those from their earnings, plus all the goodwill they lost from people saying, like, that's it, I'm not taking them anymore, et cetera, et cetera. Right? And they had to pay people refunds that had to scramble and find flights on other airlines. So what happened? Well, they had a problem with their spanning tree, with the tree that shares all of this stuff, and they ended up building a loop. And as their manufacturer, one of the suppliers for their network, we knew this and argued with them about it. And they thought they knew more about how to do it, and turns out they were wrong. But in the meantime, what the sales team had to do with our senior management was write them, their CIO, a letter saying, don't come crying to us. You're using this practice. It's against industry standard. You're putting your business at risk. We advised you against it. We urge you to reconsider. But we hold no responsibility for what happens to your network. And then the whole thing, you know, crashed around their ears. And we're like, really sorry? How many people can we send over to help you get it back up? Maybe next time you'll listen. So that's the way it's hardball sometimes out there. And the CIO lost his job, which is exactly what should have happened. We should have fired him on the spot. The average lifespan of a CIO is about 12 months, 16 months, something like that. They don't last long, and most of them shouldn't. Most of them don't know what they're doing. How many times has Google put a page up in front of you that says, just wanted to let you know that this Sunday between 1 and 4 a.m., we're going to be performing maintenance on some of our servers, and you may not be able to perform your Google search? Anyone? How many times have you had a bank do that? You ever had a bank? Your banking app, you ever see notices from them that say, Sunday morning maintenance, we're going to be down? They all do it. Fire them all. There's no reason anymore to do that if you manage your resources properly. Their problem, their only saving grace, is that they have a lot of legacy computing that does not work the way the cloud does. It's really hard to transition that stuff. So, okay, come on now. Right? All right, so these switches are extremely effective. This is the popular way of building out networks. There's some other things that we can do with it that are, you know, really pretty cool. You can sort of build fake LANs, and we'll talk about that in a moment. So here's an example of a hierarchical network. There's a router at the edge. You only send stuff to the router if it really needs to leave the campus. Otherwise, you let the switches kind of manage everything. So switches only work at layer 2. They don't do any, they don't know what IP is, or their world is totally MAC addresses. Routers are much more complicated. They have IP, and you have to have routing tables and forwarding tables and all of that stuff. Switches don't have any of that stuff. And then the hosts on the ends, of course, have applications. So this got a little spaced out funny, and so the layers don't line up right. So we'll save that out and fix it. Okay, I said a second ago that you can do some kind of fun things. This is also an extremely popular technique that's used in networks. And I guess I can make it a little easier to read here. In this case, what it shows is I've just by a miracle happened to have physically subdivided my 3 departments worth of users, each behind their own collective switch. That doesn't happen, not in most organizations. So you may have someone from the library. They park librarians inside each of the schools. They're here, they'll help you, they work with you, they're down the hall. But they have reasons to still have them have the access back to the library land because they have special programs they can run to do things like check out books, and they can print things to a special barcode printer, and those are not things that they want to just open up to the whole campus. So what they would really like is for you to have access to those things just as if you were still back at the library. And you can do that. You can build a virtual LAN, and what you'll basically do is divide the ports up on a LAN to logical different groups. And each one of these colors will act like it's a separate LAN. So what things can LANs do? Well, if somebody sends a broadcast out, all the other devices on the LAN can see it. When you look for hardware addresses, you can only see the ones on your own local LAN, right? So if you want to divide this up so there's 2 groups of users, you can do that with the switch. And then when somebody in the yellow group sends out a broadcast for an ARP reply, no one from the blue group will see it. And in fact, you can have the yellow group that's tunneled back and connected to one port on a router and the blue group to another, even though they're physically on the same switch. You also can move someone someplace else on campus. And this basically creates virtual separation. You can mix and match them here as well. In fact, you can have people that are in different parts of the campus, and they all belong to the same virtual LAN. So if I send out an ARP from device 15 on this switch, all of the yellow group ports all over campus hear it. And maybe that's everybody on campus that's part of the computer science department. They can all see it. If someone in the blue group sends out an ARP request, all the blue ports around campus could see it, for example, or just a regular IP broadcast. So this is a very helpful security mechanism. It required changing the Ethernet standard. So Ethernet frames between the switches have VLAN IDs in them, so you know which one it is. But this would be an example if you have a badge printer that prints off student badges, and it's the beginning of the school year. And so over in the Student Center, I have 20 intake registrar assistants sitting there helping get the new freshmen signed up and stuff like that. And we're taking pictures of them with our laptops, and we're sending it over to the badge printer. Probably not a good idea to put the badge printer on the local LAN inside the Student Center, because people will start printing out fake badges and things like that. So make a VLAN. Even over Wi-Fi, it will work. Every one of the Ethernet packets they send has a MAC address. Teach the Wi-Fi router to treat Ethernet frames from those MAC addresses differently from all the others. Encrypt them, tunnel them back to the registrar's office where it gets dumped back out, and when they look at the list of printers, they don't see the list of printers in the Student Center, they see the list of printers back at their office. When they open up their shared folders and shared servers, they see the ones back at their office, for example. So that turns out to be a really important security mechanism. Don't let anybody access the accounting system except for this list of MAC addresses wherever they are on campus right now, like the auditor, somebody like that. So like I mentioned, they had to change the format of the Ethernet frame a little bit, and they did. They put some extra stuff in here. So this can say like, well, which network is it I'm supposed to pretend like he belongs to? Is he supposed to be like the registrar or somebody in computer science or what? So this works out really well in shared environments also. We have different companies that are in the same kind of office space. Okay, let me look. I think that's all I have, because if we move forward, we're going to get into the next one. This is a good place to stop. Okay, any questions on this stuff? Have you guys heard of VLANs before? Anybody? Yep, okay, good. Yeah, only here. So you'll run into them in business all the time. They're used for efficiency, security, because they're cheaper than routers. They can forward things around campus without needing a router's help, et cetera. So they're here to stay. All right, I'll let you guys out a few minutes early. I went a little bit fast, and you guys got the email that no Tuesday, right? You would have gotten it too. Okay, good. Just want to make sure it went out the door. And then I'll see you guys online on Wednesday from Canada. If I'm wearing like a big fur cap and 3 layers, you know, I was going to say don't laugh, but no, I would definitely laugh at me. So you should laugh. All right, see you later, guys.